This series of presentations will help you understand what is happening behind the curtain when you use the web, email, or anything else through the internet. In this presentation, we look at how other protocols sit on top of TCP/IP, the Transmission Control Protocol and the Internet Protocol. Protocols can sit on top of one another. After a handshake, there are more protocols that let a conversation build to a more and more meaningful exchange. All internet communication is end-to-end. Two computers having a two-way conversation. For the web, one of the computers is the client and the other is the server. Remember that the two-way arrows shown in this diagram actually involve other computers along the way, as you experienced in an earlier activity, passing messages along from one end of the connection to the other. You're familiar with the client end, the applications like Safari, Internet Explorer, Firefox, and Chrome. You type in a URL that contains a domain name. Your client application gets the IP address for the server using the DNS. Then, your client opens a connection to the server. The client sends packets addressed to the server using the IP address, and the server sends packets addressed back to the client. A server program is usually called a daemon, and it runs on the server computer. For a website to stay up, the daemon program has to always be running on the server computer with uninterrupted access to the internet, listening for clients to make requests. One server can listen to hundreds of clients. Like all internet communication, computers make web requests and responses using protocols. Protocols are just mutually agreed upon standards. Committees, companies, and any group of people, they can agree on a protocol. The picture shows the protocols we will address in this lesson. They move up the ladder of abstraction as you move inward on the diagram. IP and TCP work together to carry a wide variety of payloads, including web pages with HTTP. IP addresses the packets. TCP numbers the packets. HTTP says, I want this web page. The details are not so important unless you're the one who worries about that level of abstraction. Recite these acronyms with me out loud. Saying it out loud creates new neural connections in your brain devoted to saying and thinking these phrases. TCP, Transmission Control Protocol. IP, the Internet Protocol. HTTP, the Hypertext Transfer Protocol. Then there are languages. HTML, Hypertext Markup Language, and CSS, Cascading Style Sheets. Ultimately, the goal is to exchange information between client and server. A web server sends content in the form of text, represented in binary as UTF-8 typically. The text has to be embedded inside HTML tags, shown here, for describing the content. On most web pages, the HTML also includes islands of CSS to tell the browser how to render the content, and JavaScript for making the content interactive. We'll look at those languages later. But that web content has to get from one machine to another. Any two computers on the internet can exchange packets with each other. The protocols that let them do that carry web data or any other data. The protocols that get these data from one computer to another are IP and TCP. The TCP/IP suite works together to carry a wide variety of payloads, including HTTP. IP addresses the packets. TCP numbers the packets. HTTP, one of the possible payloads, says, I want this web page, or here's that web content. The payload of the packets could have been an image, and the TCP/IP packet could have contained some other payload instead of HTTP. Maybe it's email. So what do all these protocols look like? IP takes care of the addresses. The client says, I'm 4.5.6.7, and I'm talking to 2.9.0.255. In the TCP header, the client adds, I want a web page. The server, who is 2.9.0.255, says, okay, I'm listening. The client says, okay, I'm listening too. That was the TCP handshake. More on that in a bit. But the client also puts a payload in the TCP/IP packet. The client follows HTTP protocol and says in the HTTP header, what I want is in the animals directory, and it's called elephant.jpg. The server says, I've got that web object. Here is the first of 92 parts of it. Then the server sends the page in additional packets, possibly one, but possibly hundreds. The packets travel multiple routes through the internet, getting passed along by computers along the way. After a latency, the client hears, "Here's part 2 of it, here's part 4 of it, here's part 7 of it." As they arrive out of order, the client acknowledges what's already been received. "I'm ready for part 3 of it." Of course, packet 3 was already sent, so the server will just keep on sending in order. "Here's part 12 of it, here's part 13 of it, here's part 14 of it," and so on. Several packets down the line, the client has everything up to packet 11, is missing 12, and then has 13, 14, and 15. The client reports, "I'm ready for part 12, but part 12 never arrives. With each arrival, the client repeats, "I'm ready for part 12. I'm ready for part 12. Here's part 19. I'm ready for part 12. The server finally sends part 12 again. The rest of the exchange proceeds without dropped packets. The server finally says, "Here's part 92 of it. I'm closing our connection." If the client wants anything more, it has to start all over again. "I'm 4.5.6.7 and I want a web page from 2.9.0.255. In a nutshell, that's the flavor of TCP/IP, addressing and sequencing packets, protocols designed to detect and correct for errors and drop packets. Computer users and application programmers don't have to worry about these details. So before we dig deeper into the details of TCP/IP in the next presentation, think about the big picture of the labor market. Computing is transforming society. All career paths need computing. Doctors and artists need computational thinking skills. Of the 1.4 million vacancies for computing specialists, however, the jobs are evenly split between application programmers and people who know about computing systems and networks. Application programmers don't have to worry about packet addressing and sequencing. The other half of computing specialists keep computers running smoothly and networked effectively, and some of them focus on these details. Computer users in any organization depend on network and system administrators and architects to understand how the network works. These specialists know the tools to diagnose and solve problems. At the low level of abstraction, we know that computers exchange zeros and ones to communicate. At a high level of abstraction, we don't worry about that. The further into the center of this diagram you go, the higher the level of abstraction. In the final presentation in this series, we'll dig down to the bits and bytes of the TCP/IP protocols.